We've talked a lot about quadratics. That's kind of where we ended before Christmas, which I'm sure you guys remember all of that stuff. What's a quadratic?
Squared.
Has an x squared in it. It's graphed with a parabola. We have done a little bit with x cubed back when we did parent functions and transformations. So that was like our chair. So those are both examples of polynomials. In chapter 4, we're kind of extending that into higher powers. So we might have an x to the 4th, an x to the 5th, x to the 6th. And we're really focusing on how can we figure out what the graph is going to look like from the polynomial. So when we had an x squared or x cubed, we could do transformations, but we don't have parent functions for all those higher powers of x. So we'll have to kind of figure out what we can do to get their graphs from there. So the first thing I want to run through is just a definition that we've seen before, but a good refresher. When I'm talking about a polynomial, I think I had you write this definition down one time. Okay, and it looks kind of confusing, but what it's saying, these a's are just coefficients. So you have a coefficient plus x to a power, and that power of x typically decreases, and we can have a constant at the end. So a polynomial.
It's just like, it's not that hard.
I don't get why do we, how do we make them?
I'm saying, like, they just like sneeze and
So this is just saying we have powers of x added together, essentially. How do you know what the degree is when you're looking at the polynomial?
The highest.
Yes, the highest. In this case, it would be that n. That was the highest power that we see. What are coefficients?
Just numbers.
Yep. The numbers being multiplied with x are the coefficients. So in this case, it's those a's. What is a constant?
Numbers like this one.
A term without a variable. In this case, it's that a sub 0. So just a number by itself is a constant. All right. What is the leading coefficient?
the highest.
It's the coefficient on the term with the highest power. So in this scenario, the n, x to the n, that's my highest power. So the leading coefficient would be that a sub n. It doesn't have to be the first term. You do have to look at all of them, but a lot of times it might be. And the leading term is just the entire term with the highest power.
Bless you.
A term includes both the coefficient and the variable. Okay, I'm not like putting this up here expecting you to memorize these definitions. You're not going to have, definitions on your test, but these are words you're going to hear me say, and you need to have some idea what I'm talking about. If I'm talking about a coefficient, or a leading coefficient, or a degree, we will look at those frequently. One other stipulation in this, in a polynomial, all the exponents are whole numbers. So your exponents 0, 1, 2, 3, and so on. So if it's a polynomial, you cannot have a fraction in your exponent or a decimal or a negative. They're nice, pretty whole numbers. When we graph these, just like when we looked at the graph of a quadratic or a cubic, it's a nice smooth curve. You're not going to see corners or anything like that. It's just a nice curve. Any transformation rules that we've learned before still work. That doesn't change. Any questions so far? So let's look at this example. I want to decide if these are polynomial. If they are, we'll give the degree. If they're not, we're going to say why not. So the first one, is that a polynomial? Yes. I have terms added or subtracted, all nice exponents. What would my degree be? The degree is the highest exponent.
4.
B.
No.
A square root is like what kind of power?
1/2.
1/2. Can a polynomial have a fraction for the exponent? No. So this is not a polynomial. The reason,
Can you just say no?
yes,
Oh, okay.
because it's,
I feel like I know that.
yeah, you know that.
With the phone.
7 extra letters there. Okay, so it's not because we have a fraction in the exponent. C. Okay, in a polynomial we have terms added and subtracted. So is this a polynomial? This is a polynomial, this is a polynomial, but when you divide them, is it still a polynomial? No. Another way to think about it, dividing is like having a negative exponent, and if it's a polynomial, you can't have a negative exponent. So this one is not a polynomial. Basically, if there's a variable in the denominator, so if there's a variable on the bottom, it's not going to be a polynomial. What about D? Which rule does it break? We don't have any adding or subtracting, but could, if I made all of these x's 0, 0 plus 0 plus 0, that's follows the rule. We don't have any negative exponents or fraction exponents. We don't have any variables on the bottom. So it looks a little bit weird, but this one actually is.
Word.
Now,
I don't know what it is, though.
the degree is a little bit tricky. 0, would you guys agree? 0 is the same thing as 0x, right?
Yep.
Is that the same as 0x squared
Yep.
and 0x cubed?
Mm-hmm.
So couldn't I put any x with that? So in this case, we have to say there is
Infinity.
no
Oh.
degree.
Yep.
That only happens when it's just equal to 0. Because in that case, you could really technically put any power of x with it. Now E is similar. It's still just equal to a number, so we know that it is a polynomial. But the degree is a little bit different. 8, is that the same thing as 8x? No. What would this exponent have to be?
1
0.
or 0.
Yes, because anything to the 0 power becomes 1. So this one is a degree of 0. Degree is like saying how many variables do you have. If you just have an 8, you have no x's with it. So the degree is 0.
You would never make us spoil that, right?
No, I'm not going to make you spoil that. So let's talk about shortcuts, because we don't want to multiply this all out. Would you agree that this is a polynomial? We don't have any fraction or negative exponents, no dividing. So the degree is like asking how many variables do you have? We don't want to multiply it all out, but we could think about this. This has 3 x's. This would end up with 2 of them. So altogether, that gives us 5 x's. So when they're adding and subtracting, you just look for the highest one. If it's multiplying, you have to think about if I multiply this all out, what would be the total number of x's? Everybody okay with me so far? So here's what I want you to do. Using your graphing calculator if you need to, I want you to draw me a rough sketch of each of these functions. So you've got some graph paper there, because I know how upset you guys get when I ask you to draw your own graphs. So I'm just asking you to give me a rough sketch for each of these. So x cubed, we've graphed that one before.
Chair.
Just a chair.
Just a chair. Maybe a little seat.
Alright, what about
Sit on
x
that.
to the fifth?
Slide on.
Chair.
It's another chair. How is it different?
It's a little wider.
It should be a little bit, x cubed is a little wider. X to the fifth should be a little bit steeper.
You're right.
Just a little bit skinnier, but same general shape. Alright, x to the fourth, what does that look like? Just like a parabola. Just maybe a little bit skinnier than the typical parabola. What about x to the sixth?
Also.
Also parabola, how does it compare to x to the fourth? Even skinnier. Good job making that skinnier. Okay. So look at the ones that were the same. Tell me what they had in common.
Odd. They're the same.
Okay. These two both had odd exponents, and they end up looking like chairs. X squared, x to the fourth, x to the sixth, they all kind of look like a parabola, and all of those have an even exponent. So this is actually what's called end behavior. We can know what the graph is going to look like before we ever do anything just by looking at the degree. So it's going to resemble x squared if your exponent is even, and x cubed if your exponent is odd. And as that exponent gets bigger, what happens to the graph? It gets skinnier. I'm just going to say narrows. Fewer words to make Gage happy.
What's on that skinnier?
Hey, bro. Keep me out your mouth.
Keep
my
next
mouth.
day.
All right. So now let's extend this into our end behavior. So end behavior for any polynomial is just telling us which direction the ends are pointing. Is it increasing or decreasing? And even if the polynomial has multiple terms, it's actually just the leading term that will dictate what our graph looks like. So we just have to find that term with the highest power of x, and that's going to tell us what the entire graph will look like. So if it has an even degree, all right, as long as it's a positive, so a positive x squared, a positive x to the fourth, what's it going to look like?
Regular.
Yeah. Now, if you are looking in like MathXL, it may say something like as x goes to negative infinity, f of x goes to positive infinity, and as x goes to infinity, f of x goes to infinity. And I feel like that's unnecessarily complicated. So
Miss Keller used to give us that.
we're going to be very, very scientific here in how we're going to write it. If the leading coefficient is positive, I want you to draw two arrows pointing up.
Oh, nice.
Okay? Our end behavior is up, up. Both ends are going up. What happens if I make it a negative x squared?
Down, down.
Plus minus.
Down, down.
Plus, yeah.
Yeah, it just flips our graph, so both ends are now pointing down.
Oh, yeah. That's not. Yeah.
Okay, now let's talk about the odd degree.
Oh, yeah. That's fine.
Isn't that both to be up, down? Or when you down, up, and then up?
Yeah, we have to go in order. So it looks like a chair. If you think about your chair, the left side is pointing down, and the next side is pointing up. So if the leading coefficient is positive, it's down, up. If it's negative, a negative flips the graph, so it becomes up, down. Right, and so when I ask you for end behavior, this is all I expect. 2 arrows. Tell me which directions the ends are going.
Love that.
So far, so good? So let's find the end behavior of some graphs. So if I'm looking at this polynomial, I only need to find the leading term. What's my leading term?
4x cubed.
4x cubed. That's all I'm looking at. Ignore everything else. So I see x cubed, and that tells me chair. The 4 is positive, so does it flip?
No.
So my end behavior? Down, up. Now what if you really got confused? How could you figure out your end behavior?
Graph it.
You have a graphing calculator, don't you? Could you graph it and tell me which direction the ends are pointing? Absolutely. All I'm looking at here is the negative x is 6. So an even exponent tells me it's like a parabola. The negative tells me my parabola got flipped upside down, so it's down, down. All right, what am I going to have to do on this one?
Don't say no, say
Yeah, except, do we really want to take all that time?
no.
No. We're busy people. We don't need to do that. So let's just think. We have this 3. Okay, all we're going to be worried about is the highest exponent, right? So in this case, that's an x. This one would end up with an x squared. So my leading term is going to be 3x cubed. That's all I really need. So can you tell me your end behavior from that?
Down, up.
So the cube tells me it looks like a chair. The 3 is positive, so it doesn't flip. So down, up. All right. So this one. We could start multiplying like crazy. Or we could just say, okay, I really need my highest exponent and everything. So in this one, we would get an x squared. In this one, what happens if you have x squared cubed?
X to the 6.
Power to a power, you multiply those. This one would give me x to the 4. So then if you multiply, you add 2 plus 6 plus 4, so we get 1/2 x to the 12. So what's my end behavior? A 12th is even, so it's a parabola. The 1/2 says it's still pointing up. So end behavior up. All right, so any questions on that part?
Questions on the original?
So the next one, I want you to try on your own. Using just the end behavior, you should be able to match these with the graph. So for instance, when I'm looking at the first one, which part of this polynomial do I look at for my end behavior? X to the 4th. So what's that going to do? What does that mean?
Goes up.
Both ends should be pointing up. So this one is graph C. All right, you guys do the next 3.
How you doing, Mr. Stucco?
If you guys tell me yes, you're doing all about that.
Well, there's stuff in here.
No, we're not.
Why is it blue?
All right, so this one in behavior should be what? Yeah, both ends should be pointing down, so that's graph A. All right, this one. should look like a chair. So the left should be going down and then up, so that's B. This one,
Roll to A.
that's like a chair, but then flip, so it's D. Is that okay? Let's go through
Into A.
a few more pieces here. Turning points are where the graph changes direction. Hmm. So for instance, if I drew this graph, how many turning points does it have?
1, 2, 3.
It changes direction
Yeah, 4 times.
here, because it was going up and switched to down, going down and switches to up to down,
What is
Three.
3.
I can't count.
6.
3.
Those points are maxes and mins, high and low points on our graph. Those are also called extrema.
You wear kids' pants. Hefty, extra large.
So sometimes, like on an ACT, you might be asked, find the extrema in this graph. It's just saying, tell me any maximums or minimums, any high or low points. Extreme
Because
points,
it's the two extremes.
highest or lowest.
This is weird.
There are two different classifications. There's absolute and local. Absolute is sometimes called global. And this is the highest or lowest on the entire graph. So there could only be one, the highest and lowest point on the entire graph. Think about like a parabola. We did maximum, minimum, and it had 1. It was the vertex, and it was either the highest or lowest on the entire graph. That was an absolute. A local is higher or lower than surrounding points. Not necessarily the entire graph. Local cannot be endpoints. So let's just look for a second at this graph I drew. Does it have an absolute max, highest point on the entire graph?
Yeah.
Yeah, right here, that would be the absolute max. Does it have an absolute min?
Yeah. No.
No, because these ends keep going down, so there is no lowest on the entire graph. Does it have any local mins?
Mhm.
This would be a local min. It's not the lowest point on the entire graph, but it's lower than the points surrounding it. What about local max?
Could be the same as
Yes. Yep.
Oh.
Actually, both this one and this one would be considered a local max.
'Cause
So they're both higher than the points surrounding it. So it is possible to be both the absolute and a local at the same time. All right, we will talk more about these as we go through this chapter, but let's look at an example real quick.
If you were the absolute maximum, wouldn't you also be the absolute maximum?
As long as you weren't an endpoint. All right, so I want you to identify and classify the local extreme points of F. So I'm asking you for the local max and the local min. All right, so graph F is this first one. Local max, which ordered pair is higher than the one surrounding it? CD. Okay, how many local mins do we have? 2. This is the local min, and so is this, because they're lower than the surrounding points. Alright, so now let's do the same thing for G. So local max means higher than surrounding points. So what would that be? MN. Local min. All right. Then I want any absolute. So for both graphs. So F, does it have an absolute max? No, because both ends are going up. What's my absolute min? All right, on G, this end is going up forever, so there's no absolute max. This end's going down forever, so there's no absolute min. So there is none on E. We're almost done. I'm just going to go over this last little piece and then I'm finished.
Oh, that's actually amazing.
All right, turning points. So we said these turning points are basically where we get maximums and minimums. It's where we change direction. It is actually related to the degree. So if your degree is n, you have at most n minus 1 turning points. So for instance, a parabola, x squared, that's degree 2, so it has 1 turning point. X cubed could have 2 turning points. If I said x to the 17th, how many turning points? 16. If you are looking at the graph, then it works the same way. If I look at this graph, how many turning points did it have? 3, so this had to be at least x to the 4th. This one had 2, so it had to be at least x to the 3rd. And I'm really not worried about this last one right now. We're not going to talk about it too much. All right, last thing that I wanted to touch on, x-intercepts are where the graph hits the x-axis, right? When I'm looking at how many it can have, it's the same as the degree in terms of how many. So if it's an x squared, it can have 2 x-intercepts. If it's an x to the 5th, it can touch the x-axis 5 times. Okay, if it's an x to the 10th, it can touch the x-axis 10 times. The x-intercepts and degree are the same. Turning points is 1 less than the degree. All right, in terms of the graph, the multiplicity tells you what's going to happen at your x-intercept. If your multiplicity is odd, your graph will just cross. It's going to hit that point and just keep going. So it goes through the point. And if our multiplicity is even, think about a parabola. Bounces. Okay. So as we go through this chapter, we'll start identifying x-intercepts, and is it going to go through or bounce? And that's based completely on the degree. complaining. All right.
I hope it's not worried, I'm not doing
If you would, get out your Chromebook. I posted a handout and I